Hello everyone, my name is Achilleas Xidis and I'm a PhD researcher with the Grammatio Colley Research Group at ETH Zurich. I would like to present to you our project called Data-Driven Acoustic Design, which is in collaboration with the Laboratory for Acoustics and Noise Control at EMPA, Strauss Electroacoustics and the Swiss Data Science Center. Who hasn't been in a public space or an open floor plan office where they didn't feel acoustic discomfort? Although acoustics are an integral and important part of our everyday life, we only give them the attention they deserve in cases where sound is the main protagonist. In these cases, we use physical scale models or computer simulations to assess the acoustic performance of our design. Unfortunately, acoustic scale modeling is very expensive, time-consuming, and most importantly, limits the design variations to the number of models we can build. So you can imagine that this discourages most architectural practices from including acoustic evaluation in their design workflow. And as a result, acoustic treatment is either disregarded or focuses only on noise prevention by applying simplified design guidelines. The combination of computational design and digital fabrication allows architects to design and build complex geometries and textures, which could also be used to enhance room acoustic qualities. Contrary to the use of standardized acoustic panels, digitally fabricated structures and surfaces could be an integral part of the room's surfaces, combining multiple acoustic properties and reflect the acoustic needs of the space next to them. Computer simulation methods can help us get around building expensive physical models. And while wave-based modeling can be very accurate, it is too slow for an architectural design context. Geometrical acoustic techniques, on the other hand, are faster, but they are less accurate, and most importantly, they require a low-resolution model because the assumption of geometrical acoustics is only valid when all surfaces in the model are significantly larger than the wavelength of sound, rendering them too low-res compared to the types of geometries we can design. And even when their accuracy and resolution are not a limiting factor, we do not have the appropriate coefficients for these unconventional surfaces, and we would still need to go through the lengthy process of prototyping and measuring them. And that is actually the starting point of our research project, where the idea is to design diverse acoustic surfaces, use 3D printing to fabricate them, capture their acoustic response using an automated robotic setup, post-process the measured data, and store them in a dataset. The goal then is to develop a data-driven simulation which would take a new geometry as input and would predict its acoustic response. This is what the setup looks like in reality. One robot carries a microphone on an acoustically transparent end effector and the other one a speaker. They both move along a predefined 3D measurement grid on top of a 1:10 scaled 3D printed panel, capturing input responses using a sweep sound, like the one you heard now, with frequencies between 2 and 40 kHz. The measurement grid consists of 78 measurement locations spread across 4 layers. There are 2,951 measurement combinations in total, and for each one we need around 12 seconds, which brings the total time per panel to approximately 10 hours. To define the grid size, its density and position, besides the size of our panels and the working envelope of our robots, we used Fresnel zones. On one hand, they helped us identify the surface coverage of all measurement locations, which then define the density of the grid, and on the other hand, to avoid as much as possible edge refractions. We don't only record the sweep signal, we also capture environment data that influence the speed of sound, such as temperature, humidity, and pressure. We've built a web-based interface to monitor all of this data and the robots in real time. To ensure that we have enough data for our machine learning system, we designed double-sided panels with separate geometries on each side. And by making them square, we can augment the captured data by rotating and mirroring them. To build the training set, we investigate a series of acoustic panels, starting with a variety of common architectural materials and fabrication techniques that have diffuse properties. The algorithm takes a flat mesh face, subdivides it using the corresponding topology characteristics, then applies a low-frequency deformation, which we call it the microstructure, and finally moves and rotates all faces to create the microstructure, in this case to make a brick wall. Here you can see several variations of the same typology with the same macrostructure but different microstructure. To ensure a clean and consistent dataset, all measurements are post-processed. We have 4 reference panels. A flat one that represents the maximum possible specular reflected energy with our 3D printed material. A PRD diffuser that represents the maximum possible diffusion. Then, to relate our material to the real world, we've also measured a flat wooden panel. And finally, we also measured a melamine foam panel that represents the maximum absorption. We start with the input response of the panel. Because the direct path of sound and its path through the panel are very similar in length, we are not able to remove the direct sound just by time window. That is why we capture the input response of the setup using the foam panel, which means that we only capture the direct sound. Now, if we superimpose the panels and foam's input responses, we see that they align. And finally, we can simply subtract the foam's input response from the panel's input response and get a clean one that only contains the reflected energy from the panel. Because the input response changes abruptly and very often, it is very difficult for a machine learning system to accurately predict it. For this, we needed to come up with ways to visualize and analyze the data. That's why we train our system to predict the cumulative energy over time in total and per frequency band. The cumulative energy of every panel is normalized based on the flat 3D printed reference panel. Now, if we compare the cumulative energy of a panel with a reference flat panel for the same microphone and speaker combination, the total value and the slope of the curve indicates a more diffusive panel because only 25% of the energy arrived and in a longer time. To create a diverse dataset, we continuously produce new panels from what we've learned from the already measured ones. To do this, we try to understand which parameters have an influence on sound and how. So we might want to know if shifting the bricks up and down plays a significant role, or rotating them, or changing the dimensions of the mortar, or if all the things I mentioned before have a different effect if applied randomly or follow in a pattern. For this, we need to come up with ways to visualize and analyze the data. So we developed a few different ways to visualize spatial data from 3 different layers using the total cumulative energy values. To show you these methods, let's have a look at 2 panels, a completely reflective and a completely diffusive one. In the simplest method, we visualize side by side the spatial distribution of the cumulative energy of all grid layers per frequency band for a given microphone position. On the left side, we have the flat reference panel, which, as I mentioned before, we use to normalize all measurement values. Hence, its total energy is shown as pure black. Any lighter color value represents less energy. With that in mind, we can see the primitive root diffuser on the right has in total less energy, and especially in the 3 lower frequency bands. And we can do this for every point on the grid. We also wanted to understand the directionality of the reflected energy. We visualize the magnitude of the total cumulative energy leaving from a given point towards all other measurement points. Here on the bottom right, you can see that most of the energy is escaping upwards, and for example in this location here you can see that some of the energy is escaping downwards. And like before, we can also display it per frequency bands. And of course, we can also do it in 3D. Furthermore, we can check if a panel has isotropic or anisotropic characteristics by displaying the directionality of the cumulative energy only on the X or the Y direction. Finally, because it's very difficult to always evaluate 2,951 measurements, we also came up with a more general descriptor for a panel, which is kind of an absorption coefficient. We evaluate a reflector factor R for every source-receiver combination J and for every frequency band I. In order to obtain a global descriptor for the amplification, we calculate the arithmetic mean of all, and from this, the absorption coefficient alpha for the whole panel. When displaying multiple panels at once, we can quickly compare them as a whole and identify the ones that we should compare in more detail using the visualization methods I just described. Until now, we've produced and measured 220 surfaces. As you can see on this histogram plot, the dataset as a whole has a fairly uniform distribution of absorption coefficients. This indicated that our strategies are working to produce a diverse dataset. Nevertheless, if you look at the same distribution per surface typology, we can see that some of them can be improved by generating more panels. Until the end of the project, we will focus on further enriching our dataset by generating and measuring more panels. We will also design new typologies based on the lessons learned through our data analysis process and come up with design guidelines for non-acousticians. Beyond this, we hope to create a reliable data-driven prediction tool which could be used to quickly and effortlessly evaluate surface designs. Finally, we will make the dataset publicly available to the scientific community. Thank you for your attention.